Hello students, in last session, so we are discussing about the crystal imperfections. So what is crystal imperfection and types of crystal imperfection? So there we have discussed the point imperfection. So what is point imperfection and different types of point imperfections. So continuing with that, so in this session, so I will be discussing about the line imperfection. So first one was point, what was discussed in the previous session. Second is line imperfection, and third one is surface imperfection, and last one is volume imperfection. In line imperfection, we got two types, edge imperfection and screw imperfection. Similarly, in case of surface imperfection, so we got three types, grain boundary, tilt boundary, twin boundary, and last one is volume imperfections. So we'll start with edge imperfection. So point imperfection is one where the defect is seen at one particular point. It is called as localized imperfection. If you take a crystal structure, so if this is a crystal structure, so at one particular point, so the imperfection is seen. That is point imperfection. So line imperfection. So line imperfection is one where a set of atoms in the vertical region gets imperfected or gets dispersed. So that is line imperfection. So more than one atom. So line imperfection, it is called one-dimensional imperfection. So where a set of atoms gets imperfected or gets moved from original location. So here we got two types. So edge dislocation and screw dislocation. Edge dislocation, name itself tells, so on one of the edges, the set of atoms gets dispersed. So here you can see two figures. So one is for ideal crystal, second one where edge dislocation is seen. So ideal crystal, you can observe that it is perfect where all the atoms are arranged in a systematic manner. So edge dislocation, if you observe this figure, so here this atom and this atom are getting dispersed from its original position. Means not one atom, more than one atom along this vertical axis, it is dispersed from its original location. Since this is a set of atoms are dispersed here, so there will be variation on this edge. So here you can see this perfect edges are seen. So this is a perfect edge, this is a perfect edge. Now here in this figure, this edge remains same, there is no change. So only here this set of atoms here in this region gets changed from its original position. Hence, this edge gets changed. There is change in arrangement in the atoms in this particular edge. So that is what's seen in this figure. That is called as edge dislocation. The atoms, set of atoms along the edge, that is dislocated. So in only there will be dislocation or imperfection will be seen only on that particular edge. So other edge it will be still perfect as it is seen in an ideal crystal. That is called as edge dislocation. So this concept of edge dislocation will lead to a phenomena called as slip. So slip is a phenomena due to which plastic deformation takes place. So what is deformation? Change in shape and size of the given material. When you take a material, if you apply load, so on both ends it gets deformed. So deformation, we got two types, elastic deformation and plastic deformation. So elastic deformation, if you take a rubber band, if you pull it, so if you leave it, so once again comes back to original position. That is elastic deformation. So where the material regains its original position after removing the load. Plastic deformation, which is permanent. So if you pull it even after removing the load, so it remains in the same position. That is plastic deformation. So this edge dislocation will lead to a phenomena called slip, due to which plastic deformation is seen in case of metals. Then come to the second one, screw dislocation. So screw dislocation is one where a plane of atoms in the horizontal axis gets displaced. So here you can see this is the ideal crystal. So this is the ideal crystal. This is the screw dislocated crystal. You can see this here. This, if you got two planes, so this plane is moved in this further. So this amount of vacant place will be there. This amount projection will be there. Initially it is like this, so it will move like this. So that is what's seen here. It is a ideal crystal. So you can see this edges A, D, F, E, B. So A, B, C, D, E, F, that is the edges seen. So you can see the second figure where, so this amount of projection is there. So this amount of projection will be further. So when that is a plane of atoms along the horizontal plane, it moves further, that is, it gets dislocated. So where in this region there will be a empty space, that is called as edge, that is screw dislocation. So both the cases, so it is observed that a set of atoms gets, that is, displaced from its original position. So that's why it's called one-dimensional. So one-dimensional imperfection. So two types, edge and screw dislocation. Then come to the next type. So surface inclination, surface imperfection. So surface imperfection is one where entire surface of atoms gets, on the entire surface atoms gets displaced from its original position, or it gets disturbed. That is surface imperfection. So there we have got three types: grain boundary, tilt boundary, and twin boundary. Now coming to the first one, so grain boundary. So if you take example, that is, if these are the two metal pieces, so when these edges are brought in contact, so atoms in this edge region and in this edge region, this is grain 1, this is grain 2. That's what this is the grain. If you take this as grain 1, this will be grain 2. This is grain 1, this is grain 2. They are brought together. So the atoms along this edge and this edge, it gets dispersed. So along these grains, atoms get disturbed, so that, so some of the atoms from the disturbed region, some may move towards the grain 2, some may move towards the grain 1. So this is the disturbed region. That is called as grain boundary. So grain boundary. So this edges. So atoms along this edge get disturbed. So some of the atoms move to this, some of the atoms to move to this. That is, there will be movement of atoms from the boundary region either to the grain 1 or grain 2. This is grain 1, this is grain 2. So that's how this imperfection is seen. That is called as surface imperfection. So entire region, the imperfection is seen. That is grain boundary. Second one is tilt boundary. So tilt boundary is one, it is an array of edge dislocation. So here you can see in edge dislocation at only one particular point the disturbance is seen. So it is an array. Array is nothing but group. More than one edge dislocations put together, it will be a tilt boundary. Here the angle of inclination will be very less. So here you can see this is the angle of inclination. So what is the, if this is a perfect crystal, so what is this angle? If this is a perfect crystal, this is angle. So angle of, we call that orientation angle. So here orientation angle will be very less. Hence this is also called as low angle boundary, that is imperfection. It is nothing but array of, that is, edge dislocations. Array of edge dislocations put together, so it will be a tilt boundary. You can observe the figure. So here one edge dislocation, here one more, here one more. But orientation angle will be very less. Orientation angle will be very less. So as array of edge dislocation present in a crystal structure, so then that type of this imperfection is called as tilt boundary imperfection. So once again here, surface along the entire surface there will be imperfections present. That is, atoms exchange from its original position to the new position. That is tilt boundary. Then third one is twin boundary. So twin boundary is once again a surface, that is imperfection. So what is the difference between grain boundary and twin boundary? So if you observe the figure, so this is the grain boundary region. So here once again this is the twin boundary. So this is one of the edge, this is one of the edge. So as usual, when two of the grain, this is grain 1, this is grain 2, they are brought together, and on the surface there will be interchange of atoms. So interchange will be such that, so this surface, the arrangement of atom on grain 1 will be a mirror image of grain 2, or arrangement of atoms in grain 2 will be a mirror image of grain 1. So once again this is grain 1, this is grain 2. You can observe the figure here. So here it is not similar. This is a grain 1, this is a grain 2. So this is a arrangement here, there is a change, here there is a change. There is no uniformity. So there will be difference in the arrangement of atoms in grain 1 and grain 2. That is in grain boundary. But here twin boundary, twin. So arrangement, so when there is a movement of atoms from this edge and grain 1 to grain 2, so the atoms move over together on grain 1 and grain 2 such that it will be grain 2 arrangement of atoms in the grain 2 will be a mirror image in case of grain 1. You can say similar, the arrangement will be similar here. This region is called as a twin region where the imperfection is seen, and this is a twin boundary. So this is the boundary, edges where the imperfection starts or where imperfection is seen, and this is the twin region. So it is the arrangement of atoms in the, that is grain 2 will be a mirror image in the grain 1. That is what twin, that's what it's called, twin boundaries, twin boundary. So this is grain boundary. So difference is here, that is grain structure will, the two grains will be identical, but here it is not. But in all the cases, so set of atoms gets, that is moved out, so or change their position. Hence, once again it comes under the edge, that is surface inclination, that is imperfection. So three types: grain boundary, tilt boundary, and twin boundary. And coming to the last one, so volume imperfection. So volume imperfection, so it is where we can measure the imperfection in terms of length, breadth, or thickness. So example, if you take a surface of a metal, so there will be cracks developed on it. So there will be blowholes. So it is one of the imperfections seen, blowholes. So blowholes are nothing but very small holes on the surface of the crystal structure. So we can measure its length, size, breadth, and thickness, which is visible. Cracks developed on the surface. So volume, so we can measure its volume. So that is the last type, that is imperfection, volume imperfection. So where it will be seen on the surface, example like blowholes, scratches, or impurities present on the surface, or cracks developed on the surface. So this can be measured, this can be measured. It's what is the amount of imperfection, so that can be measured. Hence it is called as volume imperfections. So these are the four types of imperfections that is seen in a crystal structure.
Yes.
In the last session we have discussed about the different type of crystal imperfections. So till now what we have discussed is starting with crystal structure, types of crystal structure. So once we know the crystal structure, imperfection, so types of imperfection, then the next concept related with this is diffusion. So in this session, so I will be covering three different concepts. What is diffusion, then diffusion types, and diffusion mechanism. So in case of imperfection, we see that so atoms move from one location to other. So then imperfection is created. So relating that, so diffusion. So what is diffusion? So diffusion is movement of atoms or molecules when they get disturbed. So movement of atoms or molecules, that is when they get disturbed. That is called as diffusion. Now, what is the necessity of studying this diffusion? Now, if you take an alloy, so alloy is where one or two metals are, suppose if you take copper and nickel alloy, so nickel will be induced into copper. So we should know at what rate the nickel atoms gets diffused into, that is copper atoms. So that is the reason why we should know this concept of diffusion. So if you want to copper nickel, nickel will be diffused. So we should know what is the time it takes and how this diffusion takes place, that is movement of atoms. So that is what diffusion, that is what diffusion. So diffusion is nothing but movement of atoms or molecules. Now here in case of diffusion, we can have two types, self-diffusion and impurity diffusion. So self-diffusion is one. If you take a metal piece, say if you take iron, if you heat it, atoms get disturbed within that crystal structure of that metal piece. So it moves from one point to other, but within that crystal structure, that is called as self-diffusion, where will be having one individual metal, one individual structure. So atoms gets moved within that structure, that is called as self-diffusion. Second one is impurity diffusion. Impurity diffusion, as I just now told, when you want an alloy, copper nickel alloy, so nickel atoms will be getting diffused into copper. So that is called as impurity type of diffusion. So for copper, nickel is in impurity atom. For copper, nickel is an impurity atom. So that is that type of diffusion where we will be having two different crystal structure. So atoms of one gets, that is, diffused into other. Atoms of one gets diffused into other. So for original structure, the second one will be an impurity atom. Hence, it is called as impurity type of diffusion. So two types of diffusion, self-diffusion and impurity type of diffusion. Now, once we know what is diffusion, types of diffusion, so diffusion is nothing but movement of atoms. So how it takes place, how the movement takes place, what is the mechanism behind that, what is the mechanism behind that, that is next topic, diffusion mechanism. So movement of atom will take place. So there should be a mechanism behind which or based on which the movement takes place. That is called as diffusion mechanism. So here the different types of diffusion mechanisms are, first one is vacancy diffusion mechanism, second one is interstitial diffusion mechanism, third one substitutional diffusion mechanism. All these things already we have discussed in case of imperfection. Vacancy, interstitial and substitutional imperfections we have discussed. Now here, based on the same concept, so diffusion takes place. So first one, vacancy diffusion mechanism. So what is vacancy? Creating a vacant spot in the crystal structure. So weak atoms moved out from its original position, that is called as vacancy. Now when a vacant spot is created, so other atom occupies that vacant spot. That is nothing but your vacancy diffusion. You can observe these two figures. So this is the first figure. This is a vacancy that is there. This is a vacant spot that is created by the imperfection. Now, when this is a vacant spot, you can observe the second figure. So here, the vacant spot, this atom moves here. So a vacant spot is created here. So that is, this vacant spot is, this vacancy diffusion is taking place because of the presence of vacancy. Because of the presence of vacancy. So originally a vacant spot is there. So these atoms in the course of time, so it moves here, so a vacant spot is created. So like that in future course of time, so this atom can come here, a vacant spot may be created. So that is nothing but movement of atoms. That is what diffusion. That is what diffusion. So movement of atoms. So if movement has to take place, one important thing is imperfection should be present. If we say that it is perfect, movement will be not there. Movement will be not there. So imperfection should be there. So due to the presence of the vacancy imperfection, so the diffusion takes place. Now here it can be, we already seen that in case of vacancy you can have one atom or two atoms, three atoms. So here just an example showing one atom, we can have two atoms. So interchanging their positions, So that is nothing but vacancy diffusion. So based on which diffusion mechanism takes place due to the presence of vacancy. Now this can be vacancy diffusion can be either by self diffusion type or impurity diffusion type. It can be within a single crystal structure or it can be more than one single structure. So it can take place either by self diffusion type or impurity diffusion type. That is vacancy diffusion mechanism. Come to the second one, interstitial diffusion mechanism. So interstitial imperfections we already discussed. So the space between the atoms is called interstitial space. So if we take crystal structure here, so this is the interstitial space. Here, 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 here. So this interstitial diffusion mechanism is one where, so you can see this is the atom, interstitial atom that is occupying the interstitial space. Originally it is here, when diffusion takes place, it moves here. In future course of time, it can move here. But it will move from one interstitial space to other interstitial space. From one interstitial space to another interstitial space. So that is nothing but movement of atom. That is what? Diffusion. That is nothing but movement of atoms. So that is what diffusion definition says. So interstitial diffusion mechanism. It will take place due to the interstitial imperfection present in the crystal structure. Here, from here it moves here, or here it has moved here, from here it can move here. So future course of time it will be moving in the crystal structure. Now this type of diffusion, that is interstitial diffusion, will be faster than vacancy diffusion mechanism. Why? Because size of the atom is smaller here. So when size is small, the movement will be faster. The rate at which the atom moves will be faster. Hence, compared with vacancy diffusion, so this interstitial diffusion is more faster. It takes place at a faster rate. That is about the interstitial diffusion mechanism. Coming to the third one, substitutional diffusion mechanism. So here one atom gets substituted for the other. So as in the same case of imperfection. So here it can be it is one atom getting substituted for the other. It can be between two atoms, it can be between three atoms, or it can be between four atoms. If you just observe the figure, so you can see this. So this atom gets here moved here, this atom gets moved. That is between two atoms. They interchange their position. Or it can be between three atoms. So this atom moves here, this atom moves here, this atom moves here. So between three atoms. Or it can be between four atoms. So this moves here, here. So one atom gets substituted for the other. One atom gets substituted for the other. So that is called as substitutional diffusion mechanism. In all the three cases, what we observe is that mechanism by which diffusion takes place. So one more concept of how diffusion takes place. So I told that according to definition it is movement of atoms. You can observe these two figures. So this is copper atom, this is nickel copper piece, this is the nickel piece. So here when you brought together, so copper atoms gets diffused into nickel, so nickel atoms diffused here. So this is the copper region, this is the nickel region. So this is the region that is diffusion takes place, where diffusion of copper, diffusion of nickel. So that is what one more concept of how diffusion takes place. The next topic is factors affecting diffusion. So we have discussed what is diffusion, diffusion mechanism and diffusion types. Now if a mechanism has to take place, there will be some factors affecting that. If a mechanism has to take place, there will be some factors affecting that. So what are the factors affecting that diffusion? So there are 6 different factors. So first one, type of diffusion mechanism. So we just now discussed types of diffusion mechanism, like vacancy diffusion, substitutional diffusion, interstitial diffusion. So here this factor, that is what type of mechanism is there, what type of mechanism by which diffusion is taking place, that affects this diffusion process. So example, if you take carbon diffusing interstitially in BCC and FCC iron. So BCC is body centered, FCC is crystal that is centered. In case of iron, material is iron. So carbon diffuses interstitially. So interstitial diffusion mechanism is one of the mechanism. So carbon diffusing into iron having BCC and that is FCC structure. It will be varying. So the rate at which diffusion takes place will be varying. That is how this diffusion mechanism affects the diffusion process. So one more, copper diffusing substitutional that is in nickel. So nickel is the atom, copper is added to nickel. So that takes place by substitutional mechanism. So what type of mechanism by which diffusion is taking place? What type of mechanism by which diffusion takes place? That defines the diffusion rate. At what rate atoms are diffusing. That is the first factor. Second one is temperature. So temperature directly proportional. So temperature directly proportional. As the temperature increases, diffusion rate also increases. So as the temperature increases, so number of weaker atoms, they start moving out. Number of weaker atoms, so rise in temperature, number of weaker atoms getting diffused. So higher the temperature, higher will be the diffusion rate. Lower the temperature, lower will be the diffusion rate. That is the second factor that is affecting the diffusion mechanism. Third one is type of crystal structure. Crystal structure, we have discussed different type of crystal structure. Simple, cubic, body centered, face centered, external closed type of crystal structure. In each type, so we have seen how the arrangement of atoms are there. How the arrangement of atoms are there. How the arrangement of atoms are there in simple cubic, body centered, face centered, like that. So the arrangement of atoms in that type of crystal structure will affect the diffusion process. So what type, if you take study the body centered FCC, that is BCC crystal structure, so what will be the rate of diffusion? If you study the FCC crystal structure, what is the rate of diffusion? It varies from crystal structure to crystal structure. Why? Because arrangement of atoms will be different. Arrangement of atom will be different in each type of crystal structure. That is once again one more the factor that affects the crystal structure. Then types of imperfection. So we just now discussed it is self type and imperfection type. We have discussed all the types of imperfection present. What type of imperfection, whether it's vacancy, whether interstitiality, whether it's substitutional. So in each case, the diffusion rate varies. Diffusion rate varies. At what rate the atoms gets moved out. Then concentration. So once again, it is directly proportional. So higher the concentration, so higher will be the diffusion rate. Lower the concentration, lower will be the diffusion rate. So once again, it is directly proportional. So the rate of diffusion is directly proportional to the concentration of atoms. Concentration of atoms in that particular type of crystal structure. And last one is atomic packing factor. So it is directly proportional. We already seen what is atomic packing factor. Suppose if you take a simple cubic, we are getting as 0.52. Means 52% of the total volume is occupied by atom, remaining is empty. So how closely the atoms are packed in the crystal structure. So higher the atomic packing factor, we have seen in a certain type of crystal structure it is 0.74. Means 74% of crystal structure is, volume of crystal structure is occupied by atom, remaining is empty. So more the empty space, so what will be the diffusion rate? So less the empty space, what will be the diffusion rate? Hence, this is one more factor that affects the diffusion rate. So these are all the factors that is affecting the diffusion rate. Affecting diffusion means diffusion rate, atomic packing factor. So if you got less space, movement of atoms will be slower. More the empty space, movement will be faster. That is what how it affects the diffusion rate. So these are the 6 different factors that affects the diffusion.